Okay, today we're going to practice a little bit with Lewis dot structures and actually putting together more complicated compounds than just binary compounds. So we said that with Lewis dot we can use the first 2 columns and the last 6 columns, our main group, representative, group A elements, and determine the number of valence electrons based on the column number that they're in. And we said we can't use it for the transition metals here in the middle, but that's not going to be the focus really of what we're talking about with bonding and using Lewis dot models in general. What we're going to focus on today is just looking at our covalent bonds, so just talking about these non-metals over on this side of my periodic table. So I want to talk a little bit more about putting together Lewis dot structures for more complicated molecules, so larger than 2 atoms within them, which we've seen in a previous video. So let's start with something that looks like this. Here's methane. Methane is one of our greenhouse gases. It is a hydrocarbon. It's a simple organic molecule. And methane is built of 1 carbon atom and 4 hydrogens. So if I look at my periodic table, I see that carbon is in column 14, or 4A, which means that it has 4 valence electrons. And when I use my Lewis dot structure, then I can see that I have 1 on each side of my structure here. Make sure those are nice and visible. And so it looks like, at least from a sharing perspective, which is what we're talking about with covalent bonds, from a sharing perspective, carbon probably wants to share with 4 things. So in methane, this is kind of handy because I have hydrogens here, and each of the hydrogens has 1 valence electron to share. Okay, so there's my 4 hydrogens, here's my 1 carbon, and now I can kind of think about how I can put them together. So let's say this one is going to come here, this one is going to come here, this one here, and this one here. So once I put them all together, then I have a structure that looks like this. I've shared a pair with that hydrogen, I've shared a pair with this one, and this one. Okay. Now we said that each of these then is a covalent bond, because a covalent bond is any sort of shared pair of electrons, and I can replace that shared pair of electrons with a hyphen or with just a dash that represents that shared pair. So in essence, I have a structure that looks like this. So this is my Lewis dot structure for methane. That would be the complete Lewis dot structure. This is just the way that it would work. That's the way it looks. Okay. Now I can have structures that aren't necessarily, that don't necessarily look like this with an atom on each side. For example, if I look at ammonia, NH3, and I go to the periodic table, then I look at nitrogen. Nitrogen is in column 15 or 5A. So when I put my valence electrons in there, I have 1 on each side, and then I have 1 that gets paired up. So there's my 5 valence electrons. Now we said before that if we already have a pair like this, this pair is a lone pair and it's unshared. So I can't add another electron in there because there's already a pair there. But I do have these 3 hydrogens with each of their individuals, so they look like just these up here. So if I have 1 hydrogen that attaches on here, 1 that shares here, 1 that shares here, then I have a structure that looks like this. Okay. Now if I replace the shared pairs of electrons with a hyphen, then my final Lewis dot structure is going to look like this, with each of my single covalent bonds represented with my hyphen, and I've maintained my lone pair here. Now you don't necessarily have to put this bubble around the lone pair like I do. I just like to show it and highlight it that way so that you know that these dots are electrons and they are already a pair. I also like it because it shows that it's taking up some amount of space, and this lone pair does take up space on an actual molecule, and we'll talk about that a little more when we talk about VSEPR structures or molecular modeling. Okay, so let's look at another example. Why don't you guys try this one on your own? So if you're playing along here at home, this is phosphorus trichloride. Phosphorus trichloride. So there's 3 chlorines and 1 phosphorus. So why don't you pause the video right here and then see if you can put together the phosphorus trichloride, and then come back and check your work as soon as I get it put together here. Okay, so go ahead and pause it right now and go ahead and work. Now that you're back, hopefully you have something that looks like this. And you'll see that each of my chlorines has 3 lone pairs on them. And it's important on a Lewis dot structure to include all of the lone pairs on all of the atoms. Now when you start to talk about 3D structures, because this is just a 2-dimensional representation of this molecule, we'll talk about the 3D structures later. When you get into 3D structures, then you don't necessarily have to show every lone pair on every atom. But when you are talking about these Lewis dot models, then you do have to show them. Okay, I'm going to show you one more example. If we look at carbon dioxide is another one of our greenhouse gases. And you look at the component pieces of it, oxygen is in column 16 or 6A, so each of my oxygens has 1, 2, 3, 4, 5, 6 valence electrons. And I'm going to draw them like this, so they're kind of mirror images of each other here. You'll see why in a second. And then my carbon, we said, already has 4. It's in column 14 or 4A. And now remember, the goal for sharing these electrons is to get to a full octet or a full valence, which in the case of carbon and oxygen is 8. It does have a normal octet. So if they were to share a pair of electrons here and here, then I would have 2 lone pairs and this pair here. That's 6, 7 on this oxygen. I'd have 2 lone pairs, this shared pair, 2, 4, 6, 7 on this one. And then my carbon would have 2, 4, 6. So I haven't quite figured out a way to put these together, because just sharing this one pair isn't going to be enough. So I may have to, and this is going to get a little messy, and I apologize in advance, I may have to share 2 pairs. So if I share this pair here and share this pair here, then if I write this in a little more organized fashion, then here's my carbon. I have 2 shared pairs and 2 lone pairs on that oxygen. Here's 2 shared pairs and then the 2 lone pairs on this oxygen. And now if we're kind of analyzing this thing, then if I look at just this oxygen, then I have 2, 4, and then the 2, 4 from the shared pair, so that's 8 total. If I look at the carbon, I have 2, 4, 6, 8 on that one. And then if we look at this oxygen, I have 2, 4, 6, 8. So everyone's happy. Now this is still kind of a mess, so I'm going to replace my shared pairs of electrons with hyphens. And now I have a structure that looks like this. And remember that when I have 2 shared pairs of electrons like this, we call this a double bond. And this is the way that the molecule is going to form in order for everyone to have a full octet, right? That's kind of the name of the game here. Okay, so this is just a little more practice drawing these Lewis dot structures, and hopefully this will help as we're moving forward, because if you can draw these Lewis dot structures, then you'll be able to go from this structure to a 3-dimensional representation of this structure using a model that's called VESPER. So look out for that video coming up next.